Hello, today we're going to talk about ABI encoding and decoding. You're going to understand in depth, in full, how it works. You're going to be able to read call data and decipher exactly what it means. And you'll even be able to construct your own call data as well. Understanding ABI encoding and decoding is a fundamentally important topic for Ethereum and Solidity developers and for blockchain developers in general. It's how all smart contracts communicate together. It's how you communicate with the smart contracts. Like, it's the language of Solidity and Ethereum. So it's like the interface between all these smart contracts, how they talk to each other, how they communicate. You need to absolutely know this to be a good developer and to be, and to become an expert. So today, I really hope that you leave this video with the feeling that you really understand ABI encoding and decoding, and you really know how to read it, and you feel much more comfortable reading it, and when you look at it on Etherscan, or just when you're auditing, or when you're developing yourself. So that's my hope. So leave your comments and suggestions in the area below, and follow and like this channel if you like this content. I'll keep producing similar educational content. Thanks for being here, and let's dive in. So here's where we need to start. ABI encoding is a way to encode data that is used to call smart contracts with. So if you have a smart contract that's deployed on chain, it's a chunk of code that lives there. It doesn't do anything. It can't do anything by itself. It needs to be activated. It needs to be called by an EOA, an externally owned account with a private key. You and I, humans, we need to put together some data to tell that smart contract to run a certain function with some arguments and so on, right? So we need to say that. So the question is, how do you do that? Do you put together a JSON with some information and send it over the network? How do you do that? The answer is you need to ABI encode the data. ABI stands for Contract Application Binary Interface. That's right here. And that's again, each smart contract has this interface. Basically, it's binary. So you're going to send a string of bits to the smart contract. So it's a binary interface, and that's how you call it. So as an example, we're going to look at this example contract. It's called foo. It has the function bar, Baz, and Sam, and that's fine. That's a legit contract, and you can deploy that on chain, and it lives there, and everything's good. The question is basically, how do we call bar? How do we call Baz? How do we call Sam? And how do we generally call the smart contract? And again, via understanding ABI encoding. You need to ABI encode the data and send it to the smart contract. And the miners or validators in general will basically take that data you send and run it against the smart contract. All right. So there's a language of smart contracts. On the docs, at the time of recording this, V820 is the latest, but in the docs, you will find this ABI spec. I have it open here in the tab too. We're going to jump to that in a second. But basically, you can see that it covers the entire design of the ABI, like how do you actually encode things and so on. We're going to cover that in full today. All right, so also note that the way things are encoded is different between call data and memory. Today, we will just focus on call data. So this is like how to put together the data that you need to call a smart contract. Fantastic. All right, so let's get into it. So first of all, I have taken some screenshots from this docs page over here. We are going to dive into this as well, because I want you to be able to, that's another thing I want you to be able to read this docs page and basically answer any questions you have about how the encoding works. Okay, so I want to make you proficient in reading this so that you can do that as well. But so I've taken a few screenshots here and there, and I will go back to the actual docs page, and we're going to read through it end to end as well. But basically, you can see here, on this docs page, at some point, it comes to function selector and argument encoding. So I'm going to go to that. So function selector and argument encoding. This is a section in the docs. You see that right here. All right. I took a screenshot of this and I put it right here. So just so you know, the point is, where does it even start? When we call a function, what happens? This is what happens. When we call a function f with parameters a1 through an, it is encoded in the following way. We need to get the function selector of f and then append to it. The way they show appending in the docs is just with a space here. Append to it the encoding of a tuple Notice the second parenthesis, a tuple, it's like a collection of items, a tuple of the arguments, A1 through AN. Notice that the return values are also encoded as this tuple, all right? So basically, in other words, I mean, this function selector is always the first 4 bytes. I think we covered that before, but like your function signature is like the function name with the arguments and so on. The function selector is like the hash of that and then the first 4 bytes of that. So what they're also saying is in terms of the arguments, right here, starting from the 5th byte, the first 4 is the selector, we're going to encode the arguments. So that's when we encode A1, A2, A3, and so on. All right. So that's just generally what happens. So you call a function, the client is going to take that function selector from whatever you send in, and then it's going to start reading the parameters. And the way you need to build it up is like you need to put the function selector first, and then you need to encode this. We're going to get into how exactly to do this. What does this mean? All right. Notice also before we get started that some of Ethereum's types, right, such as struct or enum, you see enum here, struct all the way down. Some of these types are valid in Ethereum, but they're actually not showing up in the ABI encoding. There's no such thing as called a struct in ABI encoding when you put it together. It just behaves as a tuple of things as struct, for example. Enum behaves as a uint8. Address payable behaves as an address, things like that. So just be aware that there's this section. A few key terms we need to know up front before we start diving into call data are the following. So one is, you'll see this enc all the time, ENC, that's short for encoding. And it just represents a general way of saying encode whatever is in this enc. So for example, encoding of X, enc of X. This means how to ABI encode variable X, all right? You can ask, well, so how do you do that? Well, that depends on what the variable is, all right? So they give some examples from the documentation, of course, and we'll go over them, but here's one. They tell you that if the variable X here is a uint, 8, for example, this M just means it could be anything like 8, it could be 256, it could be 32, whatever. This uint of M in general, the way you encode it, the enc of X, is the big endian encoding of X itself, padded on the higher order, meaning on the left side, with 0 bytes such that the length is 32 bytes. So the point is, encoding of X for a uint is almost X. It's almost equal to X, except for this padding stuff. And we'll get into why that is happening. But you're going to see this padding a lot throughout. You'll see this is always matched to 32 bytes. You'll see that all the time. They're going to make it match 32 bytes. So even just a number 1, they're going to pad with zeros and like have 32 bytes in just a single one. So you'll see this repeatedly. But anyway, that's the point of what this means. Why didn't they just write X? Well, if they just wrote X, there wouldn't be this padding rule here included. That would just be X. X is not padded by default. You need to tell it to pad it as well. That's what that encoding means, all right? So it's not just X. It's X padded. That's what this enc X means. I just want to make sure that's clear. So that's just the notation for that, and you can generalize that, right? We're also going to get into the context, or you'll see this a lot with the concept of head and tail. So every type, when we ABI encode it, will have a head and it will have a tail. What does that mean? Right now, that might be a little weird. We will certainly get into that. You just need to know the term. Head in general of X just means where can I find the tail of X? That's all it means. It's a way to basically punt to later on. Right now, I'm not going to put all of X. Think of more complex types than a uint, like dynamic type, like a dynamic array with a varying amount of elements. In the call data, we don't want to put it right there. Sometimes we want to actually say, oh, the head of a dynamic type means, oh, you can go find it later. You can go find the tail later. But right now, I just want to tell you where to find it. I don't want to put all the data right here. All right, so you'll see how that plays out in a minute. For static types like a uint, the head is just the encoding of the uint itself. There's no tail. Okay, so it's really just most important for dynamic types. But every type does have a head. It's just that some types don't have a tail because they're static. So just know that this seems very abstract right now. We're going to get into why. And then basically the tail again, I said head is like, where can I find the tail? And the tail is like, great, that is the actual encoding of X. All right. So you'll see this in the docs where they describe this. They're saying if you have a tuple like X with X1 through XK, the head and tail are defined for this type, like basically for x1, for example, as follows. All right. If ti is static, the head of if xi is static, then the head of xi is just the encoding of xi. And there is no tail. You see, it's empty string. There is no tail. I mean, there is a tail. It's just the empty string. Okay, so every type has a head and a tail. All right. If it's dynamic, it's much more complicated. We'll get into that later, but I just want you to know about now, what do they mean when they say encoding? So over in the docs, you're going to see this encoding referred all the time. And I don't want you to get confused. It just means just encode this. And each type is encoded differently. All right. Where do you find out? It's right here. How are the encodings done? It's right here. Formal spec of the encoding. So you can see, well, how do I encode a Boolean? Yeah. So what is enc of Boolean? Well, that's specified right here. If that type is a Boolean, you just need to do the same thing as you do for uint8, all right? And then you just need to use a 1 if it's true and 0 false. That's how you do that. That's enc of x, where x is a Boolean. Enc of x, where x is a uint_m, well, we just covered that. Enc of x, where x is a string, well, that's this up here. All right, that's how you do that. So that's just to say that. And the head of tail, we're going to see how that plays out. Cool, so those are some key terms. Now let's actually get into it. Splitting all data into head and tail is important. So if you're given a tuple, which you are when you call a function, it takes the arguments, puts them in a tuple. Remember that? So we always start with a tuple. The way to then create the encoding of that tuple is, let's say you have a tuple of t1 through tk. Okay. Now you encode this tuple by putting the head of t1, putting the head of putting the head of tk, right? So you just put the head of each element in that tuple, and then you follow it. Note that, again, the space just means append to it. Like use the bytes, you just append the bytes to it. The tail of that first element and up to the tail of that kth element. You always do that. So you always put all the heads up front and then the tails in the back. Okay, that's always the general pattern. Okay, and if the type ti is static, the head of that xi is the encoding of xi. So one note is basically they're saying that if the type behind the ith element is a static type, then the head of the actual variable is the encoding of that variable, and the tail is empty. So we've seen that before. Now, though, for it being dynamic, if it's a dynamic type, so dynamic just means it can vary in length. Like think of a dynamic array where we don't know how many elements can be added. Like you can just keep adding to it. It's not a fixed thing like a uint where it's like we know it's 1 or 4 or whatever, but it doesn't ever grow in size beyond its size. Like a uint256, it doesn't grow beyond. For a dynamic array, it can have 10 elements, 1,000 elements. It can take up many bytes, small bytes, and so on. So the point is just, that's a dynamic type. In that case, the head of the dynamic type is the encoding of the length, okay, of all the heads and all the tails up to the point where I am, like my past neighbor. So what does that mean? Well, we're going to cover it. We're going to cover an example. I'm going to visualize exactly what this statement means right here. Like, what does this line mean? We're going to cover that in detail in a second. Just know that it's a little bit different than for a static type, right? Because you're gonna get some length of something and yada yada. This just means where does that next thing start, and we'll get to that. And then the tail of this dynamic type will be just the encoding. That's where the encoding is stored. So notice for dynamic type there is a tail. For a static type there is no tail. All right. So that's all fine. So we're just gonna do a little practice now, and we'll get into the specifics. We'll visualize it too and everything. Let's say we have a function called myfunc. It has a uint256 argument a1. It has a uint8 argument a2. That means if we were to take apart and analyze the input arguments, whether they're static or dynamic, we just say, well, the first one is uint256, the next thing is uint8. Those are both static. Okay? That's just a fact. The way we then kind of dissect this argument list is we put them in a tuple. So we've kind of done that here. And then the way we operate on that tuple, remember you have a tuple here. The way you actually encode a tuple is you put all the heads first, and then you put all the tails. So what we're going to do is put all the heads first, the head of a1, right? That's the first variable. And then we're going to put the head of a2. That's all the heads first. Then we're going to put the tails, tail of a1, tail of a2. That's always true. whether it's static, dynamic, anything. You just always do this in your head at least. Put all the heads, put all the tails. Done. So this is general. Now we need to, so you can also visualize it like this. Put head of A1 here. The head always take up 32 bytes, all the heads. Okay, even irrespective of whether that type is dynamic or not, it always takes up 32 bytes. The tail, though, is what can vary quite a lot for dynamic types. But anyway, you can visualize like this, head of A1, head of A2, and then the tail. Again, I'm showing these slightly larger because they can have like a varying length. They can be very long, in fact. Like it could be the tail of A2 is like ginormous, like it goes all the way up here. All right, so just to kind of visualize it. But the heads will never change. Let's just say that's the length of 32 bytes. Okay, just so you know. So that's the way they do it. Now the question is, head of A1, what does this mean? Well, as we saw before, you need to actually encode A1 because it's a static type. Okay, so the head is the encoding itself. For a dynamic type, the tail is the encoding. Okay, so anyway, there's no tail for a static type, so that's it. Also, what was that encoding for A1? Well, we can go look here. We already did that before. How do we encode a UN? Well, we're just going to put X, but we're going to pad it to the higher order, the left side with zeros. That's how we do it. So as an example, let's say we wanted to, like that A1 was equal to 1, the value 1. How do we encode 1? Well, we do it like this. We put a 1 at the lowest byte, and then we put zeros all the way up so that this whole thing has 32 bytes in total. That's what big endian means. We're going to fill it up to the left, meaning that like the lowest byte has the highest value. So that's what that means. And then head of A2 is also a UN, is a UN 8, but that's just A2 pad to the left with zeros, right? That's it. So this enc of A1, as we already covered up front, is just a convenient mathematical way to say, just encode this. Each type has its own way to be encoded, but it's just in the docs, they can generalize it and make it easier, the discussion, when they say, just encode whatever this is. I don't care how you do it, just do it, right? So anyway, so in this case, we can actually remove the tails, you see? There's no tails. We can remove these. There's no tails in this incoming data. Here in the first head sits, okay, I'm going to move this, sits encoding of A1. That's what sits there in the head. I'm going to make this slightly, well, actually. Sits encoding of A1. Here sits the encoding of A2. Okay, that's what sits in head of A1 and head of A2. And again, what is encoding of A1? For UN256, it's 0, 0, dot, 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 and let's just say the value is 1. This is 32 bytes of data in total, and it's all zeros except that first one. In encoding of A2, let's say A2 is 10 or something, right? So it's going to look like that. All right, so that's just how it looks. That's how the call data looks. So how does the call data look? Well, let's write out the whole call data, okay? This was just the arguments. This is the encoding of the arguments. The whole call data, how would that look? Well, we're going to get our, just going to find the text here. There you go. We're going to have our function selector first, which is going to be 4 bytes. I don't know what the function selector of my func with these parameters are, but let's just say it's, A1, 2, 4, 1, 2. So 1, 2, 3, and then 4. Let's just say it's that. It's definitely not that. Let's just say it's that. The point is, this is the function selector, these 4 bytes here, okay? Each hex character is half a byte, so 2 is 1 byte. So I have 1, 2, 3, 4, right? So that's how it's going to look, 4 bytes. And then again, we're going to, let's just say the input values were 1 and 10. We're going to put 32 bytes. We're going to put a bunch of zeros here, right? And, we're just going to keep going until we have 64 of these, right? And then we're going to put a 1. This might not be 64. I don't know how many characters this is. We can use a character counter to figure that out. But the point is, that's how it'll look. I'm just roughly showing how to look. And then for the next one, we'll do the same thing. 0, 0, 0, 0, 0, 0, 0, 0, right? Keep going. 8, right? It'll definitely be longer than this, but just so you get a sense of it. This is what they mean. So if you've ever seen weird call data that looks like this, just a bunch of zeros and some stuff here, that's what this means. This is the function selector. This right here. This right here. And then that's the first argument. And then, okay, they've got to be equal in size. And that's the same argument. Again, this should be 32 bytes, not whatever I drew here. But that's the point. That's how you think about it. All right? Cool. So that's how this call data would look to call this myfunc with these arguments. All right? And that's it. Now we're gonna get into more advanced examples. We're gonna do more drawings, more visuals, but I hope you're at least now kind of getting a general sense of what's going on. We have this concept of these encodings. We have this concept of heads and tails. We haven't used the tails yet in this example, but we have the concept. We will soon, though. In fact, right now. So now we're going to do another case. So in case 2, we're going to have this function. So it's going to have a bytes input called A1 and a uint256 called A2. That means a byte and a uint8. Sorry, I wrote that wrong. uint256. So that's the 2 argument types. For bytes, we can see that definition. The following types are called dynamic. Again, so that's the ones that have a tail, where it gets a little more funky than static types, but it's called dynamic. Bytes, that's the one we have now. Great. String, which is really just the bytes underneath. Dynamic array for any t. So it doesn't matter what you put for t. You can put another dynamic thing. You can put another dynamic array for t. So you can have a dynamic array of dynamic arrays. You can also put bytes. You can also put uints. You can put wherever you want. But as long as you have these 2 brackets, that indicates a dynamic array. You can also say when you have a fixed size array of k elements, but t itself is dynamic. That's a dynamic type. And then, of course, a tuple, if any of the tuple elements are dynamic. That's what they're saying here. All other types are static. So these are the only dynamic types. So we have a dynamic type here because we have a bytes. So I just wrote dynamic and static. So that's the way in your head to kind of, you can just think of it as a static or dynamic. Great. As you know, when you call a function, the client is going to take these arguments and put it into a tuple. And then the next step is to put all the heads and then all the tails. So that's what we're doing here. Head of A1, head of A2, tail of A1, tail of A2. That's generally correct. Great. The A1 happens to be dynamic. So what happens? What is head of A1 for a dynamic type? Well, we need to go up here. This is from the documentation. And we've looked at this before. Head of xi, if ti is dynamic, is the encoding of the length of all the heads, right, from 1 to k, so all of them. And then just the tails, not all the tails, but just the tails that goes from 1 up to the element right before me. Remember, I am t. I'm the ith element in this tuple. The second element, third element, whatever it is. Take all the tails of everything before me. Okay? Again, all the heads, not just the heads before me, all the heads, and just the tails up to the element before me. Take the length of all that and encode that. Okay? How do you encode a length? Length is just treated as uint256. So when you encode a length, it's going to do that padding again. Remember, we know now how to encode a uint256. It's going to pad on the left, and it's going to just put the number. That's how you generally, when you see encoding of length, this expression, encoding of length, it's just encoding a uint256. And so it's going to pad it. Okay? And anyway, so that's that. So the thing we're going to do for the head of A1, because it's dynamic, we're going to say, I'm going to get the length of all the heads, which I have 2 heads, head of A1, head of A2, and then all the tails of elements before me. But since I am the first element in this argument list, there's no elements before me, so there are no tails I need to include in this length. Okay? So I'm just going to encode the length of the heads. That's what's going to be in head of A1 right here. Head of A2 is going to be, well, that's a static type. So we're not going to do this encoding length thing up here. We're just going to encode A2, which is, again, A2 padded to the left. So that's what's going to sit right here. And again, the tail of A2 is going to be empty, right? It's a static. However, the tail of A1, which was the bytes, is going to be the encoding of A1. That's going to sit right here. So what does this mean? You can think of it just as a pointer here, which says, or a bookmark, if you will, that says when I go to head of A1, it's going to tell me where its tail starts. So that's what this little arrow is trying to do. And that's what this length is. Because again, it's going to get the length of A1 and A2. Well, that means it's going to, the length of A1 and A2 is like from here to here. So it's going to store that here, that length, right? So in this case, it's going to be, the length of those two together, which is OX40. Okay. So OX20 is here, right? That's 32 bytes. OX40 is here. That's 64 bytes. And it's going to start right here. That's where it's going to point to. So that's what this is. Why are we doing that? Well, because we don't want to put all the data right here at an undefined length here. Okay. It's just cleaner to have all the heads next to each other and then have each head spawn out to whatever that dynamic tail is. Okay. Now, tail of A2 doesn't exist, so we could actually technically delete that, right? It's a static type. So in this case, we just have head of A1, head of A2, and tail of A1. That's all we have. So again, so in the documentation, right? When you go read this, all they're trying to say in this line is skip over all the stuff that's before me and tell me where I can start putting my dynamic data. For A1, that means skip over head A1, head of A2. I can't start putting data here. I'm going to overwrite things. I don't want to do that. Start putting things right here. There's an empty spot. That's all they're trying to say here. Okay, and then the tail of that element is the encoding of that element. So start putting it right there. Okay, that's all they mean. We're not going to go deeper into this example. We will in a second go to a great extent. I just wanted you to start understanding where this tail comes in and what it's trying to do. If we had another element that was dynamic in this list, like we had string of A2, and then we changed this to A3 or something. Now we had bytes string UN256, which is dynamic, static. Well, we still need now we need the head, just like usual. We just always do this. This is the process. And now we need the tail of A3. So how would this look? Well, we would encode a head. We always have the heads, remember? Those don't change. So we have head of A1, A2, A3. I told you before that head of A1 would be 40, but now you also have head of A3 that enters in here, right? Remember, all the heads, you got to encode all the length of all the heads. Great. So that's that. So that still starts, that now starts there at 60 this time, right? Oops, 60 right here. Okay, so that changed a little bit. And notice that we have another dynamic type as the second arc. A2 is now dynamic. It wasn't before, but now it is. So I'm changing the example a little bit on the fly here. So we're going to store in A2 where the tail of A2 starts, which is not going to be empty, right? It's a dynamic type. So we will need to make space. And let me draw it in slightly different length just because, again, they can have different lengths. So that's going to point to there. Okay, so it's going to start here, and it's going to point to right here. So that's going to point to OX60 plus the length of this tail of A1, which depends on how many elements, or how long that byte string is of A1. It could be very long. It could be 1,000 bytes. Okay, and then tail of A2 would start there. So we would store in head of A2, skip over these 3 32-byte slots, and also the 1,000 bytes that is tail 1. Okay, and then start here. All right. So do like OX60 plus 1,000 bytes, right? Which then you would have to hex encode and stuff like that. But I hope you're getting some intuition about this. It's just that's all it is. And then again, head of A3 is still static, so that's just going to store what? It's going to just store the encoding of A3, which is the encoding of a UNT, which is the left padded value. So this, if A3 is 4, let's say the value is 4, we're just going to store 4 in there. Okay? But remember with this encoding thing, right? So like that. That's all that's going to sit here. Here is going to be the length of all these things. Okay? So does that kind of make sense? We're going to do more examples. We're going to get in depth, but I want you to start building some intuition. We got these encoding things. Great. We figured that out. We got the heads and tails. Notice we always do the heads and tails. And for these function arguments, we actually do tuple. Then we process the tuple element by element, but we always construct the tuple with all the heads and all the tails. Sometimes the tails are empty. All right. That's the algorithm. That's the process. So now we're going to look at a much more advanced case here. We're gonna consider a case where there's like 2 dynamic types, or kind of, you could say not 2, but like nested dynamic types. What I meant to say. So what I mean by that is, what if you have a case kind of like over here, where you have a dynamic type, which is again this here. So that's a dynamic type that contains a dynamic type. So this is like a dynamic array, which is dynamic. It's even in the name. It's a dynamic array of bytes of dynamic types. It's a dynamic array of dynamic things. All right. So in this case, I must have copy pasted this. All right. So in this case, we have a bytes array as the first type and a UN256. That's a dynamic thing. It's a static thing. The nesting doesn't matter here because right now we don't care what this is. We're just reading it like that. It's just a dynamic array. I don't care if T is dynamic or static. So it's a dynamic array. So that's dynamic. Don't worry about it. It could be infinitely nested. Doesn't matter. But it's a bytes array and so on. Again, we're going to do the heads just like usual. We're going to do the tails just like usual. Now you can start maybe to do it in your own head. No pun intended here, right? But you can kind of start to just do this without me writing it down. Just lay out the heads, lay out the tails. Now we need to recursively apply the rules. Recursively. And that's what they're saying to up here. they're saying that, where did they say that? Yes, here. For any ABI value, we recursively define the encoding depending on the type. So what they just mean to say is that, I'll show you what the recursion means, but basically just like keep doing these same things, right? All right, so what does it mean? What is head of A1? A1 is this weird thing now, but it's not that weird. It's just a dynamic type, so we know what to do. We need to put in the head the length of all the heads and all the tails of elements before me. There are no elements before me, so there are no tails. So it's just the length of all the heads before me. And as my tail, I need to put the encoding of myself, right? So we'll see what that encoding is. For A2, it's much simpler. It's static. So the head is the encoding of it, which is, again, A2 padded to the left. We know that now for a UN 256 or any UN, really. The tail is empty, though. It doesn't exist. So we can draw it like this. We have head of A1. We have head of A2, tail of A1. Great. But let's look at what tail of A1 is, because now that includes or holds dynamic things. So how do you actually encode a dynamic array? A1 is a dynamic array. Remember, it's a dynamic array. How do you encode that? Well, you look in the docs. Okay, so you look in the docs right here, and it'll show you how to encode a dynamic array. It's right here. Remember before we looked at uint. We got this. Now we got a dynamic array. We got to look up here. All right, so how do you do that? You just, from the docs, you do this. This is x, the variable x that has type, this dynamic array, has k elements, let's say. Okay, so of course at the time when you actually call the function, although it's a dynamic array with varying elements, you know at the time of the call how many elements it has. Sure, if you call it right after and you've added some elements, k will be different, but that doesn't matter. Right when you call it, k is certainly fixed. You know how many elements it has. So k is assumed to be of type UN 256. Great. So that means the way you encode a dynamic array is the following. You encode the length, k, or the number of elements, if you will, k. And again, that's assumed to be UN 256. You know how to encode a UN 256, right? You just take the value itself and you pad it with zeros on the left. That's how you do that. So that's what you need to put first. Then after that, you need to encode a tuple. So you see now actually a tuple shows up again. A tuple with all the elements in the array. X0 is element 1. And ... x k minus 1 is the last element. So that's the kth element. And you're encoding another tuple. So that's what I mean by recursion. We started with a tuple. We started encoding each of these things in the tuple. We created the heads, the tails. In one of the tails, now is showing up another tuple, this one. And we can technically keep going like that. That tuple can hold another tuple, but it's fine. It doesn't matter. We just start over from where we know the rules. We're coding a tuple. How do we encode a tuple? We already know that. Put out the heads, put out the tails, and keep going. All right? But that's how you do it. So anyway, let's break down the tail. So again, head of A1 is just like before, is actually, because it's a dynamic array, it's going to be a dynamic type. So it's going to point over here. Let me change this. It's going to point over here to the start of tail of the start of its tail, right? And we do that right here. This points to here where its tail starts. Head of A2, because of the UN 256, we know that. 0, ... 0, let's say the value is 4. Doesn't matter. That sits here. There's no tail of head A2. Okay, so I think you get that now. But let's break down the tail. Again, as I said, what is actually then contained here for dynamic array? Well, it is the encoding of the length, which is just this, again, would be, let's say it has 2 elements. It would be like this. Because that's the encoding of k, which is 2 elements, which is UN 256, which you know how to encode. The tail itself is the encoding of a tuple. Okay, fine. So in the tail sits here. How do we dissect this? Well, we've already dealt with that. It's just another tuple. So break it apart. Again, I wrote 2 here as an integer, but technically it's padded, right? So how do you do with the tail? Well, if it has 2 elements, just take this tuple. It has 2 elements. We know how to do it. Head of x1, head of x2. x1 is the first element in that array. x2 is the second element. There's a tail for each as well. Okay? Generally speaking. Great. x1 and x2 are both dynamic themselves, actually, because it's a dynamic array of bytes. If it was a dynamic array of uints, like if, I think you get that, but let me just make that clear. If it was a dynamic array of uints, like UN 256 dynamic array, that we had taken as input to this function, all the way up here, like there. This would have been, we would have been done here because we know what the head is for UN256. X1 would be UN256 as a dynamic array of UN256. We know what the head is. That's the value itself padded. That's the value itself padded. That's empty. That's empty. Done. We were done with the encoding. The tail would just be two 32-byte chunks, each with their value, the value of those elements as UNs. Now, however, it's not a UN, it's a bytes. Okay? So we have a dynamic, and that's why this example is much more difficult in general. But so what is the head of X1 here? Well, again, we need to now skip over all the heads and all the tails of elements before me. Since I am X1, there's no elements before me, so I just need the length of all the heads. That's what gets stored in head of X1 over here. I kind of took it over here. Okay, that is what is in tail of A1. Is just head of X1, which says I start over here at the tail of A1. Okay? And so, again, the heads are just jump to where I have free space now. We covered that before. What is head of X2? Well, now I'm going to encode all the length of all the heads. I have a comma here, but in the docs, they just do a space. But I just want to make that clear when you read the docs. It's a space, but it just means concatenated together. But now I actually have a tail this time. The length, I need to get the length of the tail because there is an element before me that has a tail, which is X1. Okay? So I just need to jump over head 1. I need to jump over head 2. I need to jump over tail 1. So in other words, what I'm going to store in head of X1 or X2 is more like jump over all this stuff here from head 1 and then all the way over here. That's how the tail of A1 alone will look. It'll have this, how many elements there. And then for each element, those will have a head and tails. Okay? Now, this also means this is actually the tail encoding of a bytes, right? Like what I mean is tail of X1 is the encoding of X1. That's what's stored there, right? How do I know that? That says it right here. Because for a dynamic array, we already did the length, we did the encoding of this, we did the heads and tails. So now we have the head of X1, which is head of this bytes, and it points over here to its tail. What is in a tail of a bytes? Let's see. That is the encoding of a bytes, which is what sits there in the tail, is the encoding of K, which is the number of bytes. That's what K is. And then padded right this time is the bytes. All right, so what do I mean? I mean that right here in the tail sits the encoding of X1, okay? That in itself is, okay, I drew that down here. That in itself is right here. How many bytes, the number of bytes is stored here. Again, that is 32 bytes because it's a UN256. So I'm not drawing it to scale here. This green area would be as wide as these red ones. It's 32 bytes right here. That is the number of bytes in X1. The bytes themselves are stored next. That's what I meant. So, but it's right padded this time. So for example, it can look like this. Remember the UNs were left padded. They had 0, 0, 0, and then the value. For bytes, you put the bytes to the left and then use 0 padded to the right. That's a little bit different. But that's fine. Just remember that. There's that difference. And that's what sits in tail of A1. So this is how the whole thing looks. I mean, that's how the whole tail looks. Is that it has these heads, and those heads point to these things that have these number of bytes, and then the actual bytes. The same will happen to tail of X2, because it's also a bytes object, or type, right? Okay, that was a little bit complicated, and we will go through a full example where we actually look at real call data. But I just wanted to build this intuition. So this is what happens with recursion, is that we just say, great, we just start with whatever the tuple is that sits in the tail. The whole thing was a tuple. Now one of the tails of that whole thing contains a tuple, and we just keep breaking that apart. So let's finally take an actual example. All right. I just looked at Etherscan the other day, a few days ago, and I literally just found this very random call. I don't know what it is. I have no idea what it does, but it was calling a function called execute, and it had some input data, some call data. So I don't know, but here's the call data. The point is just I found some function that got called, and here's the call data. And I want you to now understand how to decipher this call data. The call data look like this, just a big chunk of hex characters, or you can convert those to bytes. There's just a big chunk of bytes that just got sent to the contract. It looked like this, and we're going to figure out why does it look like this, and how do we make sense of this, okay? This also means that, so again, this is the raw call data. It also means that you will be able to, after you understand how the call data looks, you will be able to technically put together your own call data and just send it to a contract. And, you don't need help. Okay, here's a point. Normally, when you go to MetaMask and Coinbase and you use all these exchanges and these tools and whatnot, they are putting this together for you. If you wanted to call this function execute here, and you wanted to call it with some input data that was the same as this, then you would technically have to put this together manually yourself. These tools like MetaMask, Coinbase, things like that, they do that for you behind the scenes, so you don't have to do it. But knowing how to do it is very valuable, as mentioned. So anyway, this looks like a mess. This is just some raw stuff here. So let's take it apart. All right. So it's ABI encoded. That's why it looks like a mess. Duh. We know that. Let's parse it. So first of all, the way to start is look at the function signature. So we know that it's the function is execute. It takes bytes. The variable is called commands. That doesn't matter. It's just a bytes. And then there's a bytes array. We already come across that. And then there's a uint256. They're called commands, inputs, and deadlines. All right. So that's the function signature. So again, just like in all the other examples, we start by constructing the tuple of type, so we know what's in there. Well, there's a bytes that's dynamic. There's a bytes array, like a dynamic bytes array that's also dynamic, and there's a uint256, which is static. Just like before, we know how to. This is the argument list. We know what to do with this. We construct all the heads. Same procedure. Head of x1, head of x2, head of x3. In a tuple, take the tail as well of x1, of x2, of x3. That's it. That's all you got to do. Now, let's start. And so we'll take those heads and tails. We'll construct it in a second. But first of all, we can isolate the function selector, which is always the first 4 bytes. Remember that? We had that all the way up here. Look at that. It's always the function selector of this function first. And then comes that encoding of that tuple. All right. So we're down here now. We're going to take the function selector, and we kind of just going to set that aside. It's not that important. It's not that interesting. We can always confirm that function selector indeed is this execute against bytes, bytes array, dynamic array, and then uint256. And indeed it is. So that's good to know. So set that aside for a second. And then again, you're going to get these. We're going to split the call data into these 32-byte chunks, because remember how it's always like padding things to 32 bytes? So it's nice to actually view the call data as split up in 32-byte chunks. That's what we're doing here, all the way down. Each row is 32 bytes. It looks like this row is shorter than the others, but that's just because it has characters that are like less wide, like narrower than the zeros. All right, but it has 32 bytes. So that's a nice way to visually show it. And then let's take a look at it. So we know that the first 3, again, the arguments is a tuple. We know we're going to put the heads as the first 3 elements, and they're going to be 32 bytes each. So we know that the first 3 rows are the heads of the arguments. Okay, so that's always true. If it had 2 arguments, that'd be 2 rows we need to focus on. 1 argument, 1 row. 0 argument, 0 rows. Right? That would be very boring. But 5 arguments, 5 rows. We always know that because the heads always come up first. All right. So the head of the first element is this, and the value is 60, and the next one is A0, and the next one is this number. Okay. So now let's see here. So now what we want to do is start to take this apart. We know that the first argument is a bytes, I believe. Yes, it's a byte. So the head of a byte, which is dynamic type, tells us where the tail starts. This says OX60. So that means this is OX20 at the end of this first row, OX40 at the end of this, OX60 at the end of this, so that the dynamic type, the first dynamic type that is called commands as a variable name, this one right here, starts right here. Like that's where its actual value starts. That's where its tail starts. Okay. And so we can kind of see this way. The 60 is showing up here as the head and is pointing to this location, which is the start of this chunk here. Okay. The A0 shows up in the head of X2 because that is also a dynamic type. And that needs to skip over all the heads, which is 60 or 60. And also the tail of X1. So that's why it doesn't become 80 or something, or X80. It needs to take into account the whole length of the tail of X1. So when it does that, it says, hey, I'm going to be starting at OXA0. That's where my tail starts. It's going to point all the way over here, technically right there. That's always A0. So let's look at the first type. Well, the first type, again, points to where its tail is because it's a dynamic type. So it says, I'm going to start at OX60. Great, let's go down to OX60. That's right here. And then that's going to be the tail. This is the tail of the bytes. And remember what that is. The encoding of the tail, the encoding of a bytes is the number of bytes, which is 2. In this case, it's just 2. That means there are 2 bytes. And then the actual bytes, write padded. Remember, bytes are write padded. So the 2 bytes are going to sit right here. 010C. Those 2 bytes, because we know they're 2 bytes, are the bytes in that bytes input. And the rest is just padded right, so that it takes up the full row here. That's it. That's why the call data looks like that for this first argument. Great. Now let's go to the next argument. The next argument is this one. That's the head of A2. And the head of A2 is a dynamic array of bytes. But for all we care now, it's just a dynamic array. So it's going to tell us where it starts. And it's going to say, oh, by the way, I start down here. Down here. Okay? And what is the encoding of a dynamic array? We can go look. So always feel free to go look at the docs. Okay? When I want you to be comfortable looking at the docs and at least be able to fish, so to speak, on your own, like figure this out on your own. So how do I encode this? What is stored in the tail of a dynamic array? In the tail of a dynamic array is stored the encoding of, that dynamic array, which is the encoding of K. K is the number of elements it has, and then the encoding of a tuple of all its elements. So we're gonna find a 2. Great, that means encoding of K is 2. There are 2 elements in this dynamic array when someone called this function. Great, what are those elements? Well, we're now going to need to encode the elements, and that's a tuple. Remember how we do a tuple? We'd put the heads, and then we put the tails. The heads tell us where the tail starts. Okay? Notice that it's a relative distance from the head to the tails. What I mean by that is, this 40 is 40 from the beginning of when we started to encode this tuple. Not an absolute distance from the very beginning of our call data. It's always relative when you start encoding tuples. So when you have these nested encodings like we have here, we started with the tuple. One of the elements of the tuples was also a tuple. That's what we're doing right now. That nested tuple is going to talk about heads and tails, and its head is going to talk about where its tail starts. It's going to be a relative thing. It's going to say, well, I'm going to talk about from where my tail starts, from when I started doing the encoding. So that's from here. So 20 is the end of this row. 40 is the end of this row, which means this is where the tail starts of that first element of the dynamic array of input. Input is the variable name of that, like up here. Right. This is a dynamic array. It happens that the types of bytes, we don't care. It's a dynamic array. And then it's called inputs. Great. So that's where that starts. The next one starts at OX160, and that's the next element in that array of inputs. And it just means that starts all the way down here. Okay, great. So far, so good. So we have the number of elements in that dynamic array is 2. Each of them are dynamic because each of them is a bytes type. That means they have a head and a tail. The head is where it starts. The tail is the encoding of it itself. So we have here, where does the first element start in that dynamic array? Where does the second element start in that array? Okay. And then when you jump to the first place, like that's now going to be the encoding of a bytes. Okay. The encoding of a bytes is how, again, we can consult the docs. The encoding of a bytes is like this. You encode how many bytes are in there, and then you pad write the bytes. So we see 100, OX100. OX100, that's how many bytes are there. Great. And then you encode you pad write the actual byte. So someone constructed this, not us, someone did this, okay? And then they ended up right here at this 48 thing, and then you just put zeros until they got to the end of that row. Because again, you always got to work in these 32 byte chunks. The point is just that this is the bytes element, basically, encoded. The length of byte, the number of bytes, and then all the bytes follows. Okay? So that's that. Now, the next element in that dynamic array starts at 160. That's what it told us up here, the head of that A2, which is also the head of inputs of 2. You can think of it as like, these are the heads of the individual elements in that array. it starts all the way down here because it had to skip over all the heads, which were up here, and also the tail of the first element, input to 0. So it starts down here, and it says, oh, I have 40 bytes. It's 40 bytes, I should say. It's hex. The first element had OX 100 bytes. That doesn't matter, whatever. We don't care. It has OX 40. Thanks for letting us know. And they look like this, and they've been padded to the right as well. Great, whatever, right? So OX 40 is two rows, right? OX 40 is the same as 64 bytes. 32 bytes, 64 bytes. That's how the elements are encoded. So that's it. That's how the whole thing fits together. And then for the third head of the original tuple, let's go back up, right? These were the 3 heads of the original tuple. Well, we still need to process this, but that is a static type. So remember that it has a head, no tail, and it's just the encoding here. Since it's a uint, we pad it on the left. So there's going to be a bunch of zeros and then the value, and that's it. We have processed the whole call data. This whole messy chunk we now understand. Okay? So I hope that was clear. Remember, in this case, we had a nesting as well going on because we had a dynamic array of dynamic types of bytes in this case. So it got a little bit complicated in that we needed to do that. So that's it, really. So the very rough mental model, I guess, at this point is like, you know that any function call, we're going to take the parameters and put in a tuple. You know that each type in that tuple is what matters. You construct a head and tail of each of those types. Put all the heads up front. Then you put the tails. So as you start processing this, you say, is the variable itself static? Great. Then in the head, I'll just store the encoding of that parameter, which again, if it's a uint, you left pad it. That's it. And I know there's no tails. You cross that out. Go to the next variable. Is it dynamic or static? It's also static. Great. Put the value, whatever that is. Because notice that it's not like all the statics. It will also tell you how to do static variables too, right? Like another static is like a Boolean, but again, that's the same as uint8. Another static is an address, but that's also like a uint, stuff like that. My point is just like, just generally be aware of how to do these static variables. But anyway, and then you go to variable 3. Oh, it's dynamic. Great. So it has a head that just points to where its tail is, right? And then in the tail, you need to then encode the actual variable itself. Right? Which for a dynamic array, you just go look here. How do I actually encode a dynamic array? It's right here. You do the length, and then you encode its elements like a tuple, and now you get this nested thing. But that's fine. So my point is just think of it as like tuple, where you go over each element, you do heads, you do tails, you parse it and like parse each of those heads, which are just encodings, and depending on static and dynamic, it has a tail or not, and so on. And then you just got to remember, of course, like the difference between padding right and padding left. You got to pad right strings and bytes. You got to pad left all these uints, things like that. And of course, when in doubt, just go look at the doc. Just go see how exactly do I encode a string? How do I encode a bytes? How do I encode a dynamic array? How do I encode a Boolean? Blah, blah, blah. Right. So my point is just, I'm just trying to boil it down into like a very simple recipe for you. Just a mental model. Great. I can construct this tuple in my head. I can create all the heads. I can create all the tails. And I know if it's static, it's just the head and it's just the encoding. And I know if it's dynamic, I need to worry about the tail, but that's fine. I can do that too, right? So now let's actually do the example from the doc. So if you scroll down on the docs here, actually right here, they give some examples, okay? So we can do that right now. Let's decode bar. How would the call data to bar look like? All right, so this is a bytes 3. Sorry, it's an array of 2 elements. So it's a fixed array. Note that. It's not just like it has a number in here. So we know how many elements at compile time is in here. So 2 elements of what? Of bytes 3. So is bytes 3 dynamic or static? Let's go look. Bytes 3. Let's see. So bytes is dynamic. All right, but that's not bytes 3. So where do we have bytes 3? We can go look here. Yeah, so you can actually see it here. So let's see. So you see this. There's an elementary type here. It has bytes of m. In this case, m is 3, so bytes 3. It's a binary type of m bytes. This is static, okay? Because again, the way to define static is basically just look at what's dynamic, and then if it's not in that list, it's static, right? But anyway, the point is that it has 3 bytes, so it's not dynamic, all right? And then, so it's a fixed size array of bytes 3, which are static elements. So it has 2 elements of these bytes, 3 things. So this whole thing is actually static. It might look a little dynamic, but it's not. It's 2 elements of something that's static. So we can kind of already now create this mental model. There's a tuple with 1 element, which is this element, whatever this is that someone sent in. It is a tuple of 1 element. We need to construct the head of that element and the tail. There's going to be, in this case, it's a static thing, so there's no tail. There's just the head. And then we need to encode that head. Like, we need to store in the head the encoding of this static type. So how do we encode a fixed size array? Well, we can go look here. The way to encode a fixed size array of any type, again, this T now is bytes 3, it doesn't matter, but it's a fixed size array with K elements. The way to encode that fixed size array is to encode a tuple of all its elements. Okay? So in this case, we need to encode a tuple of 2 bytes 3 elements. All right? So how do you encode a byte something element or whatever? That becomes a bytes 3. So the way you encode a bytes 3 is you look in the docs again, we can see it right here. Bytes of M. The way you encode X, if that is of type bytes of M, so for example, byte 3, is you just put the sequence of bytes in X padded with trailing 0 bytes to a length of 32 bytes. Okay? So the type already tells you how many bytes there are, so you don't need to specify that. We don't need to like encode S3 and then encode the bytes, because we already know it's bytes 3. So remember, we had a tuple of 1 element. That was the fixed size array. The way to encode a fixed size array is just by encoding a tuple of its elements. Right now it has 2 elements, each is a bytes 3. The way to do the first one is static, right? So you do the heads, you do the tails of these 2 elements. There are no tails. They're both static types, bytes 3. So you do the heads. How do you do a head? What do you put in the heads of the first element? It's the encoding of that element, so the encoding of a bytes 3. They just told us here the way to do an encoding of a bytes 3 is to just put the sequence of bytes, but pad it with trailing zeros. So again, you're going to write pad it. So that means you're going to put just those 3 bytes and then write pad it with zeros. We saw an example before. Then you go to that's what you put in the head, so that it's a multiple of 32. Now, of course, when you have 3 bytes, that's not going to fill up more than 32, right? So that's just 32. And then for the next element, you do the exact same thing. So in terms of how many bytes are totally involved with this call data, you need 4 bytes for the function selector. We always need that. And then you need, if you're calling a function, of course, but there are some esoteric examples, but you need the 4 bytes always. And then in this case, you need 32 bytes and you need another 32 bytes. So totally you need 68 bytes to call this function with some input, 68 bytes. And that's also what they find in the documentation. They say there's a method ID, and then you derive that from the 4 bytes of the catch-check of the signature and so on. And then the first element in their example here is 45, the next one is 1. But the point is that that's how it looks. So now you understand, again, we went through this tuple to, in this case, other tuple, because of fixed size array, you had the heads, the tails, everything, right? So you can kind of start to see that. Now let's do Baz. Baz is another function. Baz is this one here. It has a uint32 and a Boolean, okay? So again, let's try to do it without looking right now. So Baz has a uint32 and a Boolean. Great. We know it's a tuple of 2 things, a uint32 and a Boolean. We need to now do the heads and the tails. So we do the head of element, or X basically, head of X, and we do a head of Y. We do the tail of X and tail of Y. Great. They're both static, so we know we can cross out the tails. So we have the head of X and the head of Y. What is the head of X? That is the encoding of X. What is the head of Y? That is the encoding of Y. What is the encoding of uint32? Well, we know that. That is just the value of X left padded with zeros, so it takes up 32 bytes. What is the encoding of a Boolean? We kind of looked at that before, but it's a uint8, and you can see that right here if you get in doubt. You just go find the Booleans right here. It's encoded as in uint8, where 1 is used for true and 0 for false. And a uint8 is, of course, we've covered this many times now. Uint8, where to find it right here. Uint any length n is just this big endian encoding. So that's pretty straightforward, right? Baz is just that. So we know we need to call it with the 4 bytes. That's a function selector. And then we need to put 32 bytes, which represents X, and another 32 bytes, which represents Y. So that's also 68 bytes total, and we can see that down here. Okay, so that's right here. Now, how do you call Sam? Sam is, again, you put the argument in a tuple, the time it's a bytes, it's a bool, and it's a dynamic array. So we have a dynamic, we have a static, and we have a dynamic. How do we do this? We put the heads, we put the tails. So put the tail of argument 1, or put the head of argument 1, put the head of argument 2, put the head of argument 3. The head of bytes, well, in this case, it's dynamic. So it's going to tell it what we're going to store there is the place where its tail starts. For the Boolean, it's just going to be the Boolean itself, left padded. They're all going to be padded, but the Boolean is just going to be the value itself, either 1 or 0. There's not going to be a tail. And for this one, we're going to store where that starts. So that's going to start at the length of all the heads plus the length of the tail of this first argument. That's where it starts. And then we're going to basically put there the encoding of a dynamic array of static types, UNs. All right. So let's try to do it kind of mentally before we scroll down, but that's where we're going to store. So I told you the head of the first variable will be where that tail starts. What is the tail of a bytes? The tail of a bytes is the length of that bytes is going to be the first 32 bytes of that tail. And the next is going to be the bytes themselves, right padded. Okay, we covered that in an example above. Great, so that's what's stored in the tail. So how much space does that take up? Well, the length is first, so that's 32 bytes. And then depending on how many bytes there are, this will always be a multiple of 32, but there could be 32 bytes, 64, and so on. That depends on how big that is. Let's say there's only 2 bytes or something that are being sent in. Then it would take up 64 bytes, 32 for the length, and another 32 for the actual bytes, right padded with zeros. That's 64. So the point is that the tail of this last element would start after the heads, so that's 32 bytes, like 3 times, right? So it's like 32, 64, 96. And then plus 64, because that was the tail of the first element. That's where the encoding of this lives. That's where the tail of this lives, I should say. Okay. And the tail of that contains the encoding of that. So how do you encode a dynamic array of static elements? Well, the way you encode a dynamic array of static elements is you put the length, right? So we have that over here. Remember that? That's this one. You put the length, and then you encode the tuples of the elements, at tuple of the elements. But you encode that tuple. So let's say it has 2 elements. So again, we needed to put the length, that's 32 bytes, that takes us to right. Let's say there's 2. So you store 2 left padded. And then you start storing a tuple of the static elements here. So you put the heads in that tuple. You put head of X, like element 1, head of element 2, tail of element 1, tail of element 2. The tails are empty, cross them out. So the heads are just the encodings of those UNs. So that's just the values themselves, left padded. That's it. That's how it'll look. So let's do the actual example visually here so you can see. But my point is I want you to just like mentally be able to do that. Just think through that. You don't need like to visualize it. You can just see it. Makes sense. So again, Sam, let's do it over, but this time draw it out. It's a tuple of, again, dynamic, static, dynamic. The 3 heads will be lined up first, as per usual. We're going to do all the heads first, then the tails. The head of X1 will be OX60 because there are 3 heads. That's where the tail starts. The head of the second element will just be the encoding of the element itself because it's static. There's no tail. Notice there's no tail of X2 over here. And the last one will be OX60 plus the length of tail of X1, which we kind of agreed to was 64 if there are 2 if it's long enough or short enough to just take up 132 block, but generally can be a very large value. But the point is that we store here like where this starts, right? Where the third elements, where the third tail starts. Tail of X1, it's a bytes, so it'll have, from the docs here, it'll have the length as we just reasoned through, and then a padded right version of the bytes themselves, which needs to be padded to a multiple of 32. So if they're less than 30, well, if they're 32 bytes or less, it'll be just one row, one block of 32 bytes. If there's just one character more, it'll be 64. Okay, up to it then taking up 64, then there'll be 96. So, and that's how that works. And the tail of X3 that's a dynamic array of static types. So they'll also have the length of that array in tail of X3. We'll store it first as a block, as a 32 byte block. That's the length of that dynamic array. And then you'll encode all the elements of that array as a tuple. In this case, that means it's a tuple of static types. So you put out all the heads, there are going to be no tails. And the heads are just the encodings of the UNs themselves. Okay, that's what will be concatenated next to that length. All right. So what does that mean? Let's draw it out here, roughly. I'm just going to use some example numbers. Let's say that the 1, 2, 3, 4, 5, 6, 7, 8, that's the function selector, right? That's how the call data to that function would look. Again, that's not the actual selector. You'd have to figure that out, but that's the function selector. We're going to get 60, right? A 60, that's what's stored. Well, we're going to left pad it. That's what's stored here. I confused myself by writing that, but that's of course left padded. The heads are left padded. They're units, and this will also be left padded, and that will also be left padded. But what will be stored next is like 32 bytes of this, and then a 60, right? So it'll be like that. Again, this is not 32 bytes. Actually, we can figure that out, but I'm just going to write a bunch as yours. All right. I mean, there's going to be 64 characters here would make 32, but the point is that's how the call data will look. There'll be 60, and then there will be x2. X2, let's just say we call it with, what was that again? X2 is like some, just a Boolean, so it's at 1 or 0. Let's say it's true. We would pad this as well. Do a bunch of zeros here as well, and a 1 if it's true. That's how the call data would look for that. And how would the call data look for the last element? Well, it would be the length of all the heads and the tails. Now, again, I'm going to assume that you can fit in the variable there in the first. Yeah, so x0. So that's what would be stored there. And then now the tail would start of the first element. And let's say again that, it has, say, 2 bytes or something. So we would store, again, all these zeros. You would have 32 or 31 of them, and then a 2. Well, technically 63 of them, and then a 2. That means they're 2 bytes. And then you would store the 2 bytes immediately here. So you would say something like A4, 1, 1. Those are 2 bytes. And then you would write pad it to the right now, all the way so that takes up 32. Now I'm done with the tail of x1, and then there's no tail of x2, and the tail of x3 is the number of elements in, what was it again? What was it called? Yeah, and there's a UN thing, right? Let's say there are 2 elements. Great, so that's 2. And then pad it, and let's say the elements is 4. There's a 4. Let's say the elements is a 6. Like that. That's how it would look. The call data. So now you know how it would look. Again, this is definitely not the right amount of zeros, but my point is just you should be able to just kind of see this in your head, like kind of how it should be laid out. The function selector, you start with the heads, which if they're dynamic, right, you need to point to where it starts. If it's the value itself, you just put it left pad it, and then this is where the other thing starts. And then it's a bytes of 2 bytes, so that's 1, 2 bytes. Right pad it, bytes is right pad it. And so on. And then it had 2 elements, the dynamic. So that's it. So you see, this should give you an ability to just look at a function and visualize how that call data should look. And again, it can get pretty complicated if you have like nestings and nestings and nestings. But it's just a pen and paper kind of bookkeeping thing at the end of the day. It's pretty easy, when you kind of know how to do it, of course. So now you can construct call data, you can parse call data, you know everything about call data now. You're ready to go out and look at Etherscan, go look at some function calls, go try a little bit on your own, try some more static, just start simple, try some static examples, just get familiar with the process, but jump to some real example in Etherscan. I took this one and parsed it here. You just pick your own favorite example. Let me know in the comments if you have any issues with this, or if you still have issues understanding it or anything, and I can try to do a better job explaining it. But again, my mental model is tuple on the arguments, heads and tails. Dynamic types have tails, static types don't. You got to left pad these uints, you got to right pad the bytes and strings, and in general, you can look in the docs for how to pad things. Now I want to go over at the end here the entire docs and just explain to you what each section does and where you find things in the docs. So the basic design is described up top. Is just saying that, hey, this ABI is important and it's how we call functions, so please understand it. That's what we did. The function selector is explained. How do you calculate the function selector? That's explained here. Don't use spaces between variables, for example, when you compute it. That's a common mistake. The argument encoding is what we just gone through and a lot, is starting from the 5th byte, because the first 4 is the function selector. You start encoding the arguments. This encoding is used in other places, for example, for return values, even event arguments are encoded the same way, so it's great to know about. And then here are the various types. So the following elementary types exist. Great. So you can just go look up. uint8 is a type. Great. So for example, you won't find a struct in here, right? In Solidity, you can use struct, but that is not a type in ABI encoding. It actually is a tuple. But anyway, you can go through all this. And then there's the following non-fixed sized types, which are dynamic, right? So it's a bytes, it's a dynamic size, string is dynamic size, and then any type you want, but as long as it has these, it's a dynamic array. So it's also a variable type. And then you can combine types to a tuple. So we've been doing that. So just so you know. And then you can technically form tuples of tuples, arrays of tuples, and so on. We've seen that case, tuples of tuples. You can also, we haven't seen that. You could have arrays of tuples as well. Actually, we did. I believe we did. So anyway, that's how it is. Now, again, as mentioned, there are some Solidity types that don't map directly to ABI types, but we can think about them a little bit differently. Address payable is not a thing that's like anything different than just an address. As far as an ABI is concerned, a contract, when we write contract in Solidity, it's just an address in terms of how it's encoded. Enum is just uint8. Struct is a tuple and so on, right? Design criteria, sure, we're just going to skip this, but sure, feel free to read through it. And then here comes the formal spec of how to do the encoding itself, right? We've been looking at this quite a lot. So the following types are dynamic, and really anything else that's not on this list is static. And then that's what they're saying here. So we had bytes, we had strings, we had dynamic arrays, we had fixed arrays with dynamic things in it is a dynamic type. We had tuples if any of its elements is a dynamic type. And we also encountered this length concept. So you see this length thrown around down here, like for example, right here. And they're just saying, well, whenever you see this len of something, A, it's just a number of bytes in this binary string A. And the type is a uint. So you know how to encode a length. So when they write encode the length, well, the length is a uint256. So you just look at how to encode a uint256. Then for any API value, we recursively define encoding. So we encoded the tuple, which itself contained tuples. So you just recursively code that. And then you have, we knew how to do the tuples. We had to write out all the heads followed by the tails. That's how you encode that. And then the heads and tails were dependent on whether it was static, there was no tail, or if it was dynamic, you had to do the head as like skip over all the stuff before me and then put my encoding in the tail, in my tail, right? We had fixed size arrays. You just encode that as a tuple of its elements and so on. This is where you can go look at how to encode everything. And then here they're specifying the function selection argument. We already went over this too. The way to put together your call to a function, you call data, is you put the function selector of f, and then you put the encoding of the tuple of its arguments. That's what we did. And notice that the return values are encoded as a tuple of its return values, v1 through vk. And we went through the example here. So now you know how to read each of these examples. And please go through, read through this. Like they're covering into very nice detail exactly how the call data is constructed. And they have the right amount of zeros. I just kind of guessed some amount of zeros which weren't right. But, now you can read this in detail. You can read all this now and understand it. And then they're going into how events are created as well in terms of the encoding. And then how errors are encoded as well. And then the JSON format of the ABI, which is constructed here, which also actually includes the name of the parameters, which we didn't really need in the ABI encoding, if you remember. But anyway, that's just included in JSON. And they're covering tuple types. And they're just saying what I just said there, which is like, despite names are intentionally not part of the ABI, they do make a lot of sense to put in the JSON so that you can figure out what's going on. But that's just... you can see here how you would put together a JSON of this ABI, because the ABI in Solidity, we've seen this before in other videos, but is actually represented on disk as a JSON, and that's with a function name, and then all the inputs you see here, these are all the arguments, and they have names and types and all this kind of stuff, right? So that's just how you create that. Let's see. Yeah, and then they have this thing called strict mode that they're just saying that is the mode that leads to exactly the same encoding as defined in the formal spec above. Okay, great. Non-standard packed mode, we're not going to cover that, but you've seen this before, encode packed and encode. Encode packed just packs it very efficiently. The problem is just that it's it's like it can lead to some clashes if you're not careful. So be very careful if you use that. If you don't know if you should use it, you probably shouldn't use it. And then, yeah, more encoding of like index parameters in the events. So the rest of this docs is kind of how to do events and errors, all this kind of stuff, which, definitely feel free to read through it. But the core concept of the ABI encoding is like above this events here, like above this line here. This is the example and everything. So now you can go look at this docs and you will never be in doubt. How do I encode certain types? Go look here, right here. This is how you encode certain types. And you just recursively apply it. You do the tuples, you do everything we just learned today. So I hope this will help you understand fully what ABI encoding is, and you can just do it now. And the better you get, I would encourage you to even practice, just do it in your head. Don't even write it down. After you've done some examples, try to challenge yourself, do it in your head. If you run into any issues, then put it down on paper and see where you got stuck, and then try it again until you can just visualize how the call data should look without doing anything on paper. And because that'll make you very fast at reading these things. And then try to construct some call data yourself. And you can try to call a smart contract with the call data you constructed yourself. You can use many tools for that, like Web3, Ethers.js, what other tools? I think you can even do actually MetaMask. You can send like just a hex value to a contract. So I think you can do it there, I believe. But the point is just try that, to not have someone do it for you. Just do it raw yourself. That would be a good exercise. So I hope you learned something. Leave questions and comments in the section below. In the comment section below, please like this video. Please follow this channel if you like the content. I'll be putting out a lot more like this in the future. I like a very kind of thorough teaching style with the visuals and everything, but let me know if something was unclear for sure. But I really hope you walk away now thinking, all right, I think I can understand this call data, and that is actually interesting. It's very important to know about. So yeah, thank you for watching. Thank you for your time, and let me know your comments, and I'll see you next time.